Good afternoon. November 17, 2025. TELE 1022, 25. Fall. Telecommunications TELE 1022. All right. Franchise College. All right. So today we're going to have a lesson on FM modulation. Let me just start this thing here. Good. So I got two presentations. One is a supplementary, and I'm going to start with the supplementary slide session, which you can once this thing is available for you to download, you can go back and forth between these two presentations. Yeah. All right. So FM modulation, frequency modulation. Let's start with the key points, almost as a review from last time that we saw each other, but those things are important to grasp. There. All right. Frequency modulation. So in frequency modulation, the information or the intelligence is encoded onto a carrier in ways that the carrier's frequency changes in response to the changes of the intelligence amplitude. As opposed to the amplitude modulation, it would be the amplitude of the carrier changes based on the amplitude of the intelligence signal. So in this case, the amplitude of the intelligence signal is varying the frequency of the carrier signal, or sometimes you can refer to it as the resting frequency. It's important to grasp that idea, the resting frequency and the carrier, because, and we're going to get to that as we go along, in this case, the carrier is the whole thing. Here's the carrier. Here's a modulated carrier. And yes, it does have a resting frequency, which also sometimes we call it a carrier frequency. That's all I'm going to say about that for now. All right. Or maybe not. The whole power of the whole signal doesn't change. It is within this whole signal. Whereas in amplitude modulation, the power changes based on the level of modulation. So if you have a louder signal or more intelligence signal as far as amplitude of the intelligence signal, the sidebands in amplitude modulation go stronger while the carrier frequency remains constant. So the more intelligence you inject into the equation, the whole signal becomes more powerful. So the power varies as far as the old constantly varies depending on the strength of the modulating signal. In FM, the power stays because the frequency varies according to the intelligence signal. You see here, there is more intelligence voltage at this point. There's no more amplitude here. It's just that the frequency here tightens a little bit, which we have a higher frequency at this point. Over here, at this point, we would have this frequency at this moment is going to be equal to the resting frequency of the carrier. Now, as we go down with the amplitude to the negative portion, you see this waveform stretches, which means the frequency is less at this point. So in transmitter, we are having the carrier and we are modulating it and sending it out. We're causing the frequency variations in that resting frequency. And at the receiver point, we are detecting the frequency variations from the resting frequency. And then we're discriminating it into retrieving the intelligence signal again. Right? So transmission, we have this and we have that. And we are resulting in this. On the receiving end, we are receiving this, we are stripping this away, and we're getting the intelligence back. All right. So the carrier's frequency is changed by intelligence amplitude. How frequently the frequency changes, it is set by the frequency of that. So it's going to go either more often or less often. It's going to shrink and contract. And there should be one more thing here. The amplitude of the intelligence signal is going to set how far the frequency of this whole signal, which carries the whole signal, and it carries the whole thing, how far it is going to swing away from the resting frequency. Key points. All right, so here's, I just kind of grade this out here. In FM, we have constant amplitude. The carrier's frequency changes, but the amplitude stays constant. We don't care about the amplitude of the signal as far as the signal detection. As far as the signal strength, yes, at some point we do care how strong the signal is, but the amplitude should be, as I say, should be just constant all the time. It may change based on the noise interference, but the noise is going to affect the amplitude of momentary amplitude rise of the whole carrier. But on the receiving end, there's nowhere in the equation that the amplitude is considered. So that noise is going to be ignored. That is why FM is quote unquote a lot quieter in transmission than the amplitude modulation, because in amplitude, the noise affects the overall signal. All right. Compared to AM signals, FM signals are less susceptible to the amplitude-based noise and interference like lightning and electrical equipment, power lines, and whatnot. Now, the instantaneous amplitude of modulating signal directly correlates to the carrier's wave instantaneous frequency deviation. So here it is on the slide. I did that last night, and I forgot already that I did this slide. The greater frequency swing, the deviation swing or deviation, a greater frequency swing is the outcome of louder modulating signal. So if this amplitude gets higher, the frequency deviation, the deviation or the frequential deviation from the resting frequency is going to go further up and further down. So like an accordion, if you look at the time-based display, it's just going to stretch and shrink like an accordion type of a thing. Okay. Here's the term frequency variation. FM signals generally require a wider bandwidth than AM signals. Well, we're going as we go along, we're going to tackle that anyways. I'm going to repeat that. FM signals generally require wider bandwidth than AM signals. The required bandwidth is estimated by something called the Carson's rule, which states the bandwidth, and it's approximately, is 2 times the maximum frequency deviation plus the maximum modulating frequency. FM signals generally require a wider bandwidth than AM signals. So here is a repetition of that. Now, by the same token, wider bandwidth is equal to or translates into a better audio quality. With AM modulation, with the rules and regulations set in place commercially, we can transmit signals of up to 5 kilohertz. Well, so if you transmit music through it, what is the human hearing range? 20 hertz to 20 kilohertz. And we are limiting ourselves in transmission of the signals up to 15 kilohertz. So not even the full human hearing range. That's why the music on AM stations sounds like it was put through a 15 kilohertz filter. That's quality. Now, channels bandwidth for FM and for AM a single channel bandwidth is 200 kilohertz. Now, for AM is 10 kilohertz because the maximum frequency that we are allowed to put through is 5 kilohertz. So we have the upper sideband, which deviates 5 kilohertz from the carrier upwards, and the lower sideband, which deviates 5 kilohertz downwards from the carrier. Altogether, 5 plus 5, we're going to have 10 kilohertz. Okay, in AM, we have the carrier frequency, that's FFT, and we have the upper sideband, we have the lower sideband. So over here, we have 5 kilohertz. And over here also we have 5 kilohertz. This should be equal. So altogether here, of course, add those two. Between here and here, you're going to have 10 kilohertz. So that's where this thing comes from. There we go. Now, you see we here 200 kilohertz. So does it mean, what does that mean? All right, because we have 20 to 20 kilohertz human hearing range, and we have a bandwidth of 200 kilohertz. Well, the distribution of sidebands is slightly different or significantly different than AM. So a single channel, a radio channel, commercial radio channel, is 200 kilohertz in width. It actually is 150 kilohertz in width. In FM, 150 kilohertz in width. And you have here and here 25. I'm not going to write the kilohertz. 25 of guard bands just to separate that from another channel. And altogether, that is going to give you 200 kilohertz. Where's the pen here? RO. There we go. Assigned frequency band within the whole spectrum. For FM, we have somewhere roughly from 88 to 108 megahertz. And with AM, the band is 535 to 1705 kilohertz. It translates into this kind of stuff here, all right? Here's the AM band within the whole spectrum. Then there's the shortwave radio, amateurs, very high frequency TV channels, 226 here. And then here's the FM radio, and then it continues. So here is the bandwidth, 88 to 108 megahertz. And over here is 540. Different sources will tell you a different thing here. 535, see here. 540, depending where you are and who tells you what. To 1600 kilohertz. Oh, 1705. All right. So don't panic when you see those numbers slightly different sometimes. AM radio is limited to 5 kilohertz in maximum frequency by the width of the bands. We just said that upper and lower side bands. So music transmission by AM radios is of limited fidelity or limited quality. And adjacent stations could interfere with each other. That's why the transmission towers or the channels geographically are not next to each other when it comes to the great scheme of things of broadcasting, where the towers are placed and what channels the towers geographically on this planet are being placed. Because of the division of the FM band for the transmission. Okay, because of the division of the FM band for the transmission of AM stereo, the frequency limit is 15 kilohertz. So, because of the division, because we know if in AM we just have a mono signal. Yes, there are some stations that are transmitting AM in stereo, but they are a rarity. AM mostly transmits in mono, just one channel. Now with FM, you get the stereo. Each channel needs some sort of space within the spectrum of the channel. So because left and right, we are transmitting Sorry, I just have to quiet this down. Because there's no one here to pick it up. It's going to keep ringing. So just bear with it. So we are transmitting 15 kilohertz signal on the frequency modulated channels. Now, our human range is up to 20 kilohertz. So it's not perfect, but it is so close to what it should be as far as exciting our ears or ear drums that for the most part we don't notice that little 5 kilohertz difference there. That's not there, those harmonics. Of course, when you have A and B comparison, when you have direct equipment of maybe a CD quality or DVD quality sound, then you might hear the difference if you listen carefully, doing A and B comparison type of thing. But 15 kilohertz is way more than 5 kilohertz. That's why the music, plus it is in stereo. Plus it is in stereo. So the music fidelity or quality is much greater. This allows the high fidelity signal transmission. Okay, the operational bandwidth is limited to 150 kilohertz, which for guard bands, we just talked about that. Actually, FM stereo covers 106 kilohertz of that. Look up the channel subcarriers to learn more. What I'm giving you here, as far as the FM modulation, is the basics of the basics, so you can carry that further. It's just like teaching a baby how to walk. So, okay, so the baby has learned how to walk, but leave the baby downtown and see if the baby can take a bus home. All right. So I'm teaching you how to walk with this one. But if you keep following the roads I'm pointing you to, you can find out more if you want to or need to. Frequency deviation. We're going through the terminology of the frequency modulation concept. Most extreme carrier frequency shift from its center frequency. It's the frequency deviation. It's a key parameter that decides the FM signal's bandwidth. So the frequency deviation tells us how far the frequency of that signal swings out from the carrier frequency, or what's more precise, the resting point or the resting frequency. How far it swings out. And the frequency deviation is written as delta F I'm just picking up and hanging up. Whoever that is. Frequency deviation is written as delta F. And it's expressed that if the frequency swings out, because it always swings out symmetrically, we have the resting frequency, it's going to go, let's say, 75 kilohertz up, and it's going to go 75 kilohertz down. So the delta F, the deviation, is expressed in how far it swings one way, as far as a number, and it is expressed as this here. Delta F equals, if it swings out 75 kilohertz away from the center frequency or the resting frequency. Then we are expressing it as plus minus 75 kilohertz if it's a 75 kilohertz. For the commercial broadcasting, +75 gives you 150 kilohertz plus 225 kilohertz guard bands. Commercial broadcasting, that's where you hear the music from. For the wide band frequency modulation. For narrow band frequency modulation, we go up and down 30 kilohertz. And this is for two-way radios, walkie-talkies, based on FM. And the quality of the sound is pretty close to AM as far as the filtering of the sound, if you could say it that way. Modulation index. Modulation index is expressed as the M with the designation of indicator of F, or beta, Greek letter beta. It is the deviation as far as number, and that will be that one far, not both, one. So plus minus 75 kilohertz. So it will be 75 here. Divided by the intelligence frequency, the modulating frequency right here. That's the modulation index. And we just express that thing in a ratio. Right? Modulation index main importance is in how it determines the bandwidth required from the for the transmission. So it dictates the bandwidth. That's one way of using the modulation index. We can tell the bandwidth. For a narrow bandwidth, the modulation index would be typically 0.5. So the deviation, one way, or the deviation, divided by the intelligence signal, is going to give us 1:2 ratio. For wide bandwidth, or wide band frequency modulation, the modulation index would be typically greater than 1. So in this case, unlike amplitude modulation, the modulation index can be more than 1. It could be greater than 1. In general, a higher modulation index leads to improved signal-to-noise ratio and increased resilience to interference and noise. Spectral content, the quantity of an amplitude of the significant sideband frequencies, okay? Quantity of, I wrote it down last night. Quantity and the amplitude of significant sideband frequencies. And we're going to talk about what it means that we have significant sideband frequencies. Because the carrier swings out smoothly from the resting point to wherever it swings out, let's say 75 kilohertz upwards and 75 kilohertz downwards. In between those points, Excuse me, I gotta tell them to stop calling, okay? Okay. The beauty of technology now. All right. Where were we? Spectral. The quantity of the, okay, so let's see here. We'll just draw something here for you. There we go. You see, in AM, you have a carrier, and we do have a sideband and a sideband, and maybe you're going to have sideband, and some frequencies here present. It's got some harmonics and whatnot. Now, if you look at this is the FFT, but if you look at time domain, and here's the frequency. This thing swings out from here to here. Now, how many points do we have? If we divide things into so many different points, so we have 1, 2, 3, 4, 5, 1, 2, 3, from here to here, okay? 1, 2, 3, 4, 5 points. Okay, divide everything in half. And I got 1, 2, 3, 4, 10 points, right? Now, there's always going to be some point in between because this thing swings smoothly. All right, that means it will have indefinite number of or infinite number of sidebands. Erase. Okay. And we are back to our laser thing. All right. So the quantity and amplitude of significant sidebands. Now, when in FM, when the sidebands swing away from the resting point upwards and downwards, as they deviate further, they become weaker to the point that, yes, they still exist, but they're so weak that we consider them insignificant. And with different modulation index, we're going to get to that. With different modulation index, we have established a number based on the modulation index. We have established a number of significant sidebands, and we'll get to it as we go along today. So the quantity and amplitude of significant sideband frequencies formed around the carrier frequency are dictated by the modulation index. I might as well let you in on where is that slide? Here's that slide. Okay. So with the modulation index of 1, we have the strength of the resting frequency. And sometimes it's called carrier resting frequency, but this is called carrier, and this whole thing is also called carrier, including the sidebands. So we have 1, 2, 3 significant sidebands. With the modulation index of 3, we have, here's the carrier or the resting frequency, 1, 2, 3, 4, 5, 6 sidebands that actually matter. We'll get to it. Bessel functions are a mathematical way, Bessel functions are a mathematical way to calculate these sidebands. I'll show you what it looks like. The carrier signal amplitude can drop to 0 for some particular modulation index with all the power contained in the sidebands. Let me just show you that slide again. Let's say where the carrier, see if signal is not modulated, the modulation index is 0, then all the power is in that resting frequency. We go up in index here. Where is it? Oh, look at that. Index about 2.4 approximately. You see, the resting frequency contains no power in it. All the power is in the sidebands. Yeah. And this is the power reference compared to the signal of reference. So if we have a 1 kilowatt transmitter times 1, the carrier here, we will have 1 kilowatt of the whole total signal. And those are fractions that we're going to use to see the sidebands. So over here, you see, the power of the resting frequency is going to be nil or null. That's what we call the first null carrier. We go back, we go up again, we go keep going. Oh, here's a second carrier null. That's the second time the carrier disappears. Does it mean there's something wrong with the signal? Are you going to hear any difference? No. It's just how technically on an oscilloscope or a spectrum analyzer, those sidebands are going to appear. And it's perfectly fine. There's nothing wrong with the signal. It's just the way the FM signal behaves. Based on the modulation index, the power distribution between the sidebands and the resting frequency, they're just distributed as they are. Okay? Propagation. VHF frequencies travel via line of sight. Compared to the wider range of AM signals, which can bounce off the ionosphere, AM doesn't need line of sight. It can bounce because so there are different frequencies. Then line of sight. So the range is typically shorter for for FM. And also FM can be affected by obstructions, like mountains or large structures. All right, you can read that later here. Noise immunity, only the frequency variations in FM signal deliver the information. Limiter circuits are used by the FM receivers to clip any amplitude changes, noise spikes, eliminating most of the signal's noise. So we just talked about that. Any amplitude changes, spikes caused by lightning, power lines, motors, whatnot, they're being ignored because amplitude is not recognized by the frequency modulating receiver. This leads to better sound quality, and particularly in case of music, when it matters for us human ears the most. That means it's the last slide of this slide presentation here. High fidelity audio broadcasting applications. High fidelity audio broadcasting, and it's between, we will already talked about those bands. TV sound transmission, two-way radio systems, various digital communications like frequency shift keying, and you can read what that is here. Due to noise resistance and signal quality. All right, and that's that. Oops. Here. Let's keep going with this presentation. All right, so we already went over this. This could be a standalone presentation, so some of that stuff is going to be repeated. We're going to skip those slides rather quicker. AM, amplitude, FM, frequencies being recognized, frequency deviations. AM vulnerability, we already talked about this. If there's a spike in AM, it's being heard on the radio. If there's a spike which affects amplitude of the frequency modulated signal, well, it's not going to be heard. Okay. Okay. History, amplitude modulation became widely used for broadcast systems in 1920s. For AM systems, the bandwidth is twice the highest intelligence. Yep. Bandwidth. Again, here's the carrier. Oh, stop. Here's the carrier. And here is the intelligence signal of, let's say, the highest signal that we're going to transmit in this particular signal is going to be, let's say, 3 kilohertz. I don't know, those lines, horizontal lines, just keep appearing on their own. Here. AM. White on white doesn't work. AM. Here's the resting frequency. Here's the carrier frequency. Let's say here's 3 kilohertz. In order to transmit 3 kilohertz sine wave, we need plus and minus 3 kilohertz. That gives us 6. Twice the bandwidth needed for transmission of 3 kilohertz sine wave is twice as much as the intelligence signal. Okay, that's what I was trying to accomplish here. Let me erase the damn thing here. Apologize. Eraser. All right. All right, so bandwidth is twice as much as the highest intelligence signal. And increased modulation increases the total power transmitted, because we talked about that already. One of the drawbacks of 2 a.m. is susceptible to noise. Da da da. See, this one's gonna go quick. The maximum. Where is this thing? The maximum baseband frequency allowed for AM is 5 kilohertz. I'm not going to spend too much time. Baseband versus broadband. If you want to punch that in Google, differences between baseband and broadband. We already talked about that when we talked about the coaxial cables versus the baseband and broadband. So and the bandwidth required, of course, because it's the 5 kilohertz. 10 kilohertz is the bandwidth for AM. But if you run your music through a filter that is up to 5 kilohertz, that's what you're going to hear on AM. That's why the music on AM sounds like it does. Channels are spaced 10 kilohertz apart, but adjacent channels cannot correlate geographically, just to avoid some accidental funny things from happening. The desire for high fidelity alternate with greater noise resistance led to development of frequency modulation FM. The first broadcast system went on air in 1939. However, FM modulation was used for two-way communications, like two-way radios. First generation cell phones, 1939. Yeah. Frequency and angle modulation. Both frequency and angle modulation are similar. With the frequency modulation, the carrier varies. The frequency of the carrier is varied based on the intelligent signal. So the frequency, okay, we got that already. Whenever the frequency of the carrier changes, there's also a change in phase or an angle and shift in phase angle, which causes instantaneous frequency change. So we can modulate by shifting the phase as well of the signal. Now, much like amplitude modulation, frequency modulation FM, or phase modulation involves multiplying the lower frequency intelligence by the carrier. Read that 5 times if you want. Unlike AM, the carrier frequency amplitude does not remain constant in AM. Right? A modulated FM carrier has an infinite number of sidebands. We talked about that. Another very significant difference is that amplitude of the unmodulated and modulated carrier in FM does not change as the result of the modulation process. The total power in FM modulated carrier is distributed among the carrier and the sidebands. So here, this is one of the, see, it's kind of on the bottom, this sentence, but it's important to understand that. It's important to not look over that sentence here. Just it's important to notice that. Let's read that again. The total power in FM modulated carrier is distributed among the carrier and the sidebands. So in FM, the resting frequency is the carrier. There's a carrier wave, and that wave shrinks or expands having different wavelengths, and by the same token, as a result, having different frequencies. The whole signal is the carrier. But also, the resting frequency, we also call that a carrier. Right? I'm leading you onto something here. FM generation and deviation. A very simple FM generator can be constructed as an LC tank circuit, sound waves. So you can have a capacitor microphone. Here's a tank circuit parallel with the oscillator. And if you vary the resonating frequency of that tank circuit, then the whole frequency, it's going to affect the whole outcome of the whole two frequencies combined. And you're going to have on the antenna, you're going to have an FM modulated signal, which would be a wave that deviates from its resting point up and down. All right. Or you can just have something that changes the phase of the signal, because not always you're going to have microphone, and then you're going to accomplish the same thing. So the frequency of the sound wave determines the rate. Okay. The rate of the frequency changes and the amplitude of the sound wave's amount of deviation. So the output frequency at any given point, instantaneous output frequency at any given point in time, is going to be the carrier frequency plus whatever the frequency at that moment is of the intelligence signal. And of course, when we have a voice transmission or music transmission, there's going to be a lot of those frequencies there present. Okay, we're going to go back to this formula sometime. A sinusoidal waveform with a peak of 100 millivolts at the frequency of 1000 hertz is used to modulate the carrier of, sorry, here's a sinusoidal waveform, peak to peak voltage 100 millivolts. At the frequency of 1 kilohertz, and that thing modulates a carrier, whatever that carrier is, at the rate of 100 hertz per 10 millivolts. So if the waveform goes up 10 millivolts, that carrier will change its frequency by 10 millivolt, 100 hertz. Find the frequency deviation and the rate at which the carrier is being deviated. Well, let's do it again here. I think we did this last time. What is the rate at which the frequency is going to deviate? Well, frequency is 1000 hertz, so it's going to deviate 1000 times per second. So the second question is answered pretty much right on the spot. Now, what else do we need to find out? Find the frequency deviation and the rate. So the rate we got, let's see, frequency deviation. It deviates 100 hertz per 10 millivolts. Okay. Now, we have positive frequency deviation because it swings out that way as far as frequency, and also it deviates that way, same amount. All right, so we have 100 millivolts peak to peak. So a peak of that is going to deviate the frequency one way, and the negative peak is going to deviate the other way. So we have two peaks, one positive, one negative. So it deviates 50 millivolts that way, 50 millivolts that way, at the rate of 100 hertz per 10 millivolts. So positive frequency deviation will be 50, half of the 100 here, millivolts, times the rate at which it deviates the frequency. So 50 millivolts is going to give us 500 hertz positive deviation. Whatever the carrier is, we don't care. It's going to go 500 hertz plus. And the negative deviation will be minus 50 millivolts times the rate. It's going to give us another 500 to the left. Altogether is going to go plus 500 minus 500,000 hertz frequency deviation. Total deviation is 100 hertz, 1000 hertz, but it's normally expressed as the delta of plus minus 500 hertz. Excuse me. Get a sip of coffee here. We consider FM broadcast station transmitting at 99.9 megahertz, which is the carrier frequency or the resting frequency, the tunable, the lockable frequency, this frequency of that station. It will only broadcast at exactly this frequency only in the absence of modulating signal, which means the antenna is going to transmit a 99.9 megahertz when there is quiet on the microphone, silence on the microphone. All right. As soon as there is a modulating signal, the broadcast frequencies will be different than the carrier and changing based on the modulating signal. The carrier will also be transmitted under most conditions, but the carrier or the resting frequency level, the power level, will change. So yes, the resting frequency level will go down, but the power of the carrier is not changing, is constant. So that might confuse some people because we have a like double meaning going on here. We say that the resting frequency is the carrier, but we also say that the deviated, modulated carrier with all its sidebands, we also call it a carrier because it carries the whole signal. So we call it a modulated carrier. Point is that the total power of the whatever is at the resting frequency plus its sidebands, the whole sum is not going to change. It's based on the deviation, based on the frequencies present. The power might be distributed a little bit different between the resting frequency and the sidebands, but always the sum of the resting frequency and all the sidebands, that is always going to be of whatever the power is. That number is not going to change. Whether the channel is going to get somebody is speaking louder or quieter, the power is still the same. Now, of course, when you run the audio signal through an audio amplifier, yeah, if it's a louder signal, the power. But we're not talking about that. We're just talking about the transmission of the signal between one antenna and the other antenna, between the transmitting and the receiving antenna. All right. An FM signal varies between 99.89 and 99.91 megahertz. megahertz, and has the center frequency of 99.9. All right, let's see here. We do this. Okay. We have the resting frequency of center frequency 99.9 here. And we have 99.89. And over here, we have 99.91. And that is in megahertz. All right. That's what they're trying to tell us here. FM signal varies. And it's swinging between two frequencies at the rate of 1 kilohertz, 1,000 times per second. Find the intelligence frequency. Okay. The rate of change is 1,000 hertz. Therefore, the intelligence frequency is 1,000 hertz. All right. And what is the deviation? Well, it is megahertz. If you do the math between here and here, you're going to have 10,000 hertz. And over here, you're going to have 10,000 hertz. So it's plus and minus 10,000 hertz, which is 20,000 hertz. Total frequency deviation, but the deviation is we're expressing, but swing one way. Time domain, we already seen that in the other presentation, but let's say the carrier has maximum frequency deviation at T2 and T4. Maximum frequency deviation. So if the amplitude goes to the maximum, that frequency of that referential frequency or the carrier frequency is going to change to the maximum in that particular case. Over here, it's not going to change, that frequency is not going to change more. Now we come back where it's going to change less. At this point, it's going to be that resting frequency. And then at that point, it's going to change the other way. So here's going to be a tighter frequency, maximum frequency, and that's going to be the minimum frequency of the whole transmission. Amplitude of the modulated carrier never changes. Yeah, that thing's not going to change, it's just the frequency changes. And the maximum frequency change is caused by the modulating frequency is, okay, and the maximum frequency change is caused by the modulating frequency is the delta. Well, delta is the change. Frequency domain here. Okay, we're going back to the modulation index. The equation for the instantaneous voltage of a frequency modulated signal is, well, here's a sine wave equation. So here's the whatever the level of the signal we are dealing with, the referential level, times the sine of angular velocity of the carrier, that omega angular velocity, if it's in radians. If you want to go in degrees, you're going to be 2 pi f. and add the time to it or multiply it by the time. Plus the modulating index or index of modulation times sine of the angular velocity with a reference to time. Here's the peak value. And of course, we already know that. This also we can express as beta. There are two ways of expressing it, and they mean the same thing. Modulating index, MF. The term modulating index is defined as modulating index for FM and is the measure of how much the carrier is varied by the intelligence signal or the modulating signal, in other words. Delta is the maximum shift caused by the modulating signal, measured in hertz or kilohertz. A plus minus 3 kilohertz deviation would have the modulating index or the deviation, sorry, of 3 kilohertz. Remember that. We're calculating that, or all the formulas are going to be based on calculating how much it swings one way. Yeah, here's a, unlike AM modulating index, the FM modulation index can exceed 1. Which has the effect on increasing of the occupied bandwidth. All right, next. Oh, here is the Bessel function, or Bessel. Expanding the expression, of course, for FM modulated carrier results in a Bessel function, which results in an infinite number of frequencies with varying amplitude. Infinite number of frequencies or sidebands. Here is the expression that we had. This slide right here. Right, instantaneous voltage. So we have that, carry that. Now, the function of the carrier versus time. Here's the first element that would be the carrier or component of the whole thing. That would be the value of the first component or the function of the first component. What does that mean, that J? See, here's J, 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 J. If the J is 0.98, it is the 0.98 of the value with reference to 1. If this was 1 watt, then this carrier, if the whole power of the whole signal is 1 watt, then in this case here, when there's zero modulation, then the component of the resting frequency would have the power of 1 watt. Let's go somewhere close to half. Let's say this is approximately half. If the modulating index is 1.5, then if the total power was 10 watts, for example, then 0.5 watts will be sitting at the resting frequency power, and the rest is distributed over the significant side bands. With the modulating index greater than 1. I wonder if you add all these. Are you going to get that? Don't know. All right. All right. So here are all the components. This is a modulating index times cosine of the angular velocity versus time. So here is that minus the first element or the first side band and all this mess that's here, plus the second side band and all that mess here, minus the third band. See, sometimes you get pluses, sometimes you get minuses. Now look here. And see here, J0 is in certain phase here. The phase changes. Approximately when this thing goes up, some of them keep going down. So that's why some of them are going to have pluses and some of them have minuses. Not going to spend too much time on that because who's got the energy? But if you want to, go ahead. Now let's keep going here. At first look, it would appear that this modulation scheme with an infinite number of sidebands and frequencies would not be very useful. But there's always the but, right? It turns out that as the sidebands move out from the carrier, the amount of power in each sideband drops rather quickly. And since there is little power, we can ignore very small sidebands. They just play no role. We can see from the formula that the magnitude of the sidebands depend on the modulating index. The magnitude of the sidebands depend on the modulating index. See, the modulating index is always there. Right? So lower modulating index will have less power in the sidebands. If that number is lower, it's a multiplication. Multiplication here. Here's the magnitude of the sideband. As we go along, they do get smaller. All right. Common value for a test deviation in voice system is that the delta is plus or minus 3 kilohertz with the modulating frequency of 1 kilohertz, which is center of our voice band, which gives us the modulating index of 3.0. How does that happen? Well, modulating index equals, which is the modulating index, is the deviation over the frequency of the carrier, or sorry, of the is that going to be better? No, it's not going to. There you go. It's just the way this thing are being displayed here. So I'm going to make a difference here. No. All right, so here you can see it. So a common test value for test deviation in voice systems is that the deviation is plus minus 3 kilohertz with 1 kilohertz modulating signal, which is going to be here 3 kilohertz is the deviation, which is the delta, see, plus minus 3. So it's altogether 6. It swings between minus 3 and plus 3, but we are only considering the upper swing or one side, magnitude of one side. So here's going to be 3 divided by what? 1. Both are kilohertz, so the units are going to cancel, and that is going to give us Mr. Bach. There are 3 kinds of people in this world: the ones who can count and the ones who can't. That's going to give us 3. All right. Here. Now it jives. Next is the slide. All right. FM spectrum and Bessel function. Here's the Bessel function, right here. In figure on the left. Here's the left and here's the figure. Now things are getting interesting. We can see the spectrum and normalized voltages for different modulation indexes. All right. Notice how quickly the sidebends drop off away from the carrier. Here and here and here. But depending on the different modulating index, see, they're not dropping like uniformly here. See, there's here, this one goes lower and this one jumps and goes down again. So things are happening interestingly here. At modulating index of 0.5, the power sitting in the carrier or the resting frequency is sitting at 0.94 of fraction of the whole transmitted power. But again, I keep saying that they call this carrier day. So this is carrier, and the whole thing is also a carrier. So just keep that in mind, because when they say power of the carrier remains constant, they mean that the power of the whole signal remains constant, because the carrier is the wave that changes in frequency, deviates up and down. It carries the whole thing on one waveform. But they also call this carrier. So you just have to kind of turn that kind of a filter on in your head when you look at what's being said at that moment. Sometimes things have different way of having logic, if that's a sentence. All right. Notice how the carrier voltage also changes, and at the modulating index of 2.5, it is almost 0. Where is 2.5? 2.5. See, that carries almost 0. So the whole power of the whole system is conserved. It's just the power is distributed with different sidebands. and the sidebands steal the power from the resting frequency. And as the modulating index increases, that thing might come back and it's going to be a different distribution and so on. Again, I say probably the fifth time right now. There's nothing wrong with that. This frequency is just how the whole fireball that is being thrown forward behaves. It just kind of like it's morphing as it travels. And all the information that's needed to be there is there. When you're listening to a radio, when that thing is changing in the different various ways, it's supposed to be doing that. Negative values of the J represent signals which are phase shifted of 900 180 degrees. Okay. The spectrum shown in each chart is for a single modulating frequency with a constant amplitude. For voice, this would be a case of the sidebands would constantly changing with frequency power, so it's going to be a mess. This thing would look like a fluid kind of a thing going on. Right? All right. Now, based on this function, here is the table that we have. And this table tells us, for our calculations, how many sidebands are actually significant, beyond which whatever is there is, well, insignificant, okay? Plays no role. Excuse me. So, when the modulating index is 0, which means the carrier or the resting frequency or the carrier is not modulated. There's only one significant frequency that is there, and is the frequency of the carrier. There is nothing else even present. There could be some garbage noise there, but so small that it's not even considered a signal. And if you tune onto the radio station of whatever the frequency is, and if nobody is talking to the microphone and no music is playing, there's just silence on the radio station, you're going to hear silence. And all the power of the whole transmitting system is going to be concentrated in the carrier frequency. Now, when things are going to be modulating, which means that somebody's going to talk louder or someone's going to talk quieter, so that's going to change the modulating index, which is going to cause, if I'm talking louder in FM, I would swing that frequency further from its resting point. And if I'm talking quieter, I'm going to swing that frequency less from its resting point. Depending on how loud I talk, I'm going to create different amount of significant sidebands. This is how loud I talk. This is how many sidebands that are of significance are being created as I go along. So at one point of volume, like if I were able to produce a sine wave with my mouth, if the modulating index is, let's say, 0.5, then Then the sidebands are going to steal the power. The sidebands are going to appear. Significant sidebands are going to appear, and they're going to steal the power from the main carrier or the resting frequency. And based on that function, this table was produced. Now, let's see if we can find the carrier nulls here. That means what all the power is in the sidebands. Oh, here's first one. At about 2.4, modulation index of 2.4. Is there another one? Oh, there's another one. So that's the first carrier null. And if we keep growing with the modulation, there's going to be the second carrier null. And if we keep going with the modulation, that's going to be the third carrier null as far as this table carries. There is a website here. I wonder if that's for the textbook. All right, how much energy do we have? We got about 20 minutes left. Are you guys awake? Does anybody respect? Kind of, somewhat. Yes, all right. Raise your hands up in the air, stretch. We've been talking for about an hour and a half right now. So let me tell you a joke. A guy walks into a bar full of people and he stands right in the middle. And he says, "Hello, people, this is me." And they looked at him and it wasn't him. There we go. All right. Here's back with his bad jokes. That's my trade. I don't know if I'm amusing myself or no, or what with this thing. I say one of those things, I look at real reactions. All right. Here's an example here. Using the Bessel function chart, this one here. Calculate using the Bessel function chart and table. This is a chart and table. We can calculate the bandwidth of the FM signal if we know the frequency of the modulating signal and the deviation, which is one-way swing, right? Right. Okay, let's see if we can do this thing here. Calculate the bandwidth required to transmit an FM signal when we are shooting 10 kilohertz into it as intelligence. And also we are shooting 5. So we got two examples. Calculate for the intelligence of 10 kilohertz and calculate for the intelligence of 5 kilohertz, both of them separately, but the deviation is 20 kilohertz. All right. What's the deviation? Where's the deviation? Here is the deviation, right here. Here's the intelligence signal. So based on that, we can find out what the modulating or modulation index is. We have this. What is that? Deviation is 20 kilohertz. What's the, for this one here, what's the intelligence? 10 kilohertz. Okay, well, 20 kilohertz divided by 10 kilohertz is going to give us 2 right? Okay. So look at the chart. Modulation index of 2. We have 1, 2, 3, 4 significant sidebends. All the other ones are so weak. They exist, but they're so weak that they are kind of like ignorable. So we have 1, 2, 3, 4 times the modulating signal frequency. All right, let's see here. This is the 4th significant sideband with the index of 2. So here's the frequency of the carrier times 2 times 2 times 3, 1, 2, 3, 4 times 1, 2, 3, 4 times 4. And that's it. So for 10 kilohertz, four times 10 kilohertz, because it's the 4th significant sideband. The 10 kilohertz times 4 is 40 kilohertz. So the deviation is plus minus 40. Kilohertz. So plus 40 minus 40, the bandwidth required to transmit 10 kilohertz is 80 kilohertz of bandwidth required for that. All right, we need 80 kilohertz space to carry on with 10 kilohertz sine wave. And transport that thing onto the other end of the link. Now, for 5 kilohertz, the deviation here is 20 kilohertz. Calculate the bandwidth required. And with the delta of 20 kilohertz, so 20 minus 20. 20. All right, so we got 5 of the intelligence signal. It goes here, 5. 20 divided by 5, because here's the 20 here, divided by 5 gives us 4. The modulation index is 4. Right here. How many sidebends? 1, 2, 3, 4, 5, 6, 7 sidebends. So it's the 7 times the modulating signal right here, sitting right here. See how weak that thing is already? 0.02 off. That's 2% of the whole total power is in that sideband. So again, how many? Oh, here's 7. All right. Ooh, here. So 7 times 5 is 3 kilohertz. So it's going to swing out, 35 kilohertz. 7 times 5 is 35 kilohertz. So the furthest is going to swing with that is going to be the bandwidth that's needed is going to give us plus and minus 35 kilohertz, because we need the space of 35 kilohertz one way, 35 kilohertz the other way, because this is just so it happens. If it swings one way, it swings the other way. Then we need 70 kilohertz of space in the bandwidth to transmit 5 kilohertz signal. All right. We can see that unlike AM, where the bandwidth is equal to 2 times the highest frequency in AM of the modulating signal, with FM, there are many more sidebands, and we need to consider their magnitude using the Bessel function, not just the simple calculation, to determine the bandwidth. We consider sidebands to be significant if they are 1% or more of the reference of the unmodulated signal. So if that is 1, it's the function of the transmitted power. So if the transmitted power is 1,000 watts, it will be 1,000 watts times 1. And here's the percentage of 1 here. So here, 1%. Now, the next one will be less than 1%, insignificant. Here's 2%. The next one is going to be less than 1%, insignificant, and so on. See, there's no one smaller than 1% here. FAM. 438. Okay, we keep going. FM spectrum and power calculations. Okay. We can use the Bessel function table to calculate the power at any sideband, keeping in mind the values in the table are V2 over V1. So it's the V2 over, well, so it's the voltage. We're doing 20 log. If it's power, then we're going to 10 log. But when we have the voltages, we're going to V2 over V1. Reference the voltage ratio here. Now, I put this thing in red with an asterisk right here. You see here, it says the power of FM carrier is constant. That's true. When they say that, is as the whole thing is the carrier. The power or the value of the resting frequency is going to vary. So sometimes they mean this as the carrier, and in some sentences they mean this as the whole carrier of the signal. Just have to watch for that. So the power of the FM signal or carrier signal is constant. Right? Is constant. And it does not change with the modulation. If you have more modulation, the power is still going to be the same of the signal. The antenna is going to transmit 1,000 watts. And if you speak quieter, the transmitter is going to transmit 1,000 watts. If you really shout through the microphone, the power transmitter is going to transmit 1,000 watts, right? If that's the strength of the signal. And it does not depend on the modulating frequency. Or in some matter of fact, nor will it depend on the magnitude of the modulating signal. Example. Let's see example here. For a modulation index of 1 and 2, find the carrier power. All right. So for a modulation index of 1, We get the power in dB reference power to the reference signal will be 20 log of the voltage ratios. Where did we get this from? Well, modulation index of 1. Let's go back. 1. And the resting frequency, we got 0.77. That's the ratio of the power that sits in that component right here, which is the resting frequency, with the reference to the signal as if it were not modulated at all. This is the actual value, magnitude of the voltage at the index of whatever it is, to the reference of a carrier or the resting frequency component if it were not modulated at all. So, modulating index of 1, we got this ratio is that the voltage to the other voltage is 0.77. Plug that in. And it's because it's voltages. We use the number 20. Log that. So it's going to give us minus 2.27. So the power of the signal is going to be 2.27 dBs below the power reference. So if it's 1,000 watts, it's going to be 2.27 dB with a reference below a power reference. For modulation signal 2, the ratio is 0.22. We plug in that into this formula, and that's going to give us the power of the resting frequency, or the whole carrier, as a matter of fact, is going to be 13 dBs below the power level. Actually, the resting frequency right here. What else can we calculate? We can also calculate the power level for each of the higher order sidebands, keeping in mind that they come in pairs, because they do come in pairs. There's upper sideband and there's a lower sideband to all that, always appearing. Upper sideband, lower sideband. Upper sideband, lower sideband. All right. For 10 kilowatts transmitter, determine the power of the carrier and the sidebands. Oh my God. Yeah, so we can see the whole thing here. For 10 kilowatts FM transmitter, determine the power of the carrier and the sidebands when modulating index is 0.2.5, 1/4. Since the power is proportional to the voltage squared, all right, we're going to have to square that voltage reference. and then multiply it by the 10 kilowatts. So where do we get that 0.98 modulation index of 0.2.5? Right here, 0.98 from this table right here. Power, V squared over R, remember? So that reference squared times 10 kilowatts. Because we have 10 kilowatts transmitter. So that's the fraction of that. So that is as much is going to be in the resting frequency. How many sidebands do we have? Only one. Right here. So times one. Right over here. And that sideband, that one sideband, is worth 0.12 of the total power. So 0.12 times, it will give us about 144 watts. Do the math. Power since in the first component of the J0 resting frequency plus the power in the sideband. So here plus here plus another one because we have two of those, right? Upper and lower sideband. Gives us this number, which is pretty darn close to 10 kilowatts. All right. We're going to stop here. How many slides do we have? And those are a little bit easier. There are a couple of calculations that we're going to do, but I'm going to leave that for Friday. Okay. Where are we here? We finished at this one here with the red thing here. Well, I'm gonna look at it. Cool. I'm gonna release that test because time is running out. Thank you for asking. Excellent question. I'm glad you asked. I gotta release that test this week, and it's going to be same way as and the quizzes are going to be short and sweet. Okay, they're not worth much anyways, so they're going to be as much as they're worth. Okay. Thank you, guys and gals, for staying up. I commend you for it, and I commend myself for doing this. Plus, I also get paid. Yeah, thank you. Have a good day. All right. See you on Friday or during the week with the lab. Oh, I gotta release the lab as well for the FM modulation. Good night. Stop recording here first.